Hello, chemistry gang. In this lecture, we are looking at titrations. In our prior lecture, we did a strong titration. And in this lecture, we are going to do a weak, strong titration. And so this is just giving, rise to, what we're titrating and what we're using as the titrant. So we could have a weak acid that we're titrating, and then we would use a strong base titrant for that type of titration. Or we could have the flip of that, where we have a very weak base that we're titrating, and in order to do that, we would have to use a strong acid titrant. So we always have this connectivity as far as, opposite chemistry, acid and base, but also we always have to have basically the strong titrant, and that's to ensure 100% conversion from our starting materials to our product. And then we have the molecule that is being titrated. And so this could be weak or strong. So what we're titrating could be weak or strong, but what's, imperative is that our titrant is extremely strong to ensure that 100% conversion. So our example for the weak strong is as follows, right? We want to sketch the titration curve for the titration of 50 milliliters of 0.1 molar acetic acid with 0.1 molar sodium hydroxide. We want to use the following data points. So for part A would be 0 milliliters, part B 35 milliliters, part C 50 milliliters, and part D at 65 milliliters of 0.1 molar sodium hydroxide has been added. So there's our question. We want to sketch a titration curve for the titration of acetic acid with sodium hydroxide. And if we look at the question, we have here, we have a weak acid, right? And that's what we are titrating. We can get that weak acid from the structure, see the CO2H. We could also get that from the Ka. Which we have here at the bottom. The Ka is 1.78 times 10 to the negative fifth. So So we know it's a weak acid not only from structure, but also the fact that it's a Ka given. And then we also have our strong titrant, or in this case, our strong base titrant. So that's the setup for the the setup for the titration. We have a weak acid, acetic acid, which are titrating. We're titrating that with a strong base titrant, sodium hydroxide, and so that is the weak, strong scenario as far as the titration is concerned. For part A, we're at 0 milliliters of the 0.1 molar sodium hydroxide. So we haven't started the titration as of yet. All right, so this is the beginning or the initial for the titration. And as we go through these different parts, the one question we want to keep asking ourselves through each part is, what do I have initial? And here, initially, we just have this 50 milliliters of 0.1 molar acetic acid. So this is really just a weak acid question with regards to our pH. Right, all we have is acetic acid. It's a weak acid because of Ka. So we can then go forward and use our methodology, of 1, which would be, okay, what's the equilibrium reaction? And then 2, well then what does our Ka actually equal to? So if we start with our equilibrium reaction, we would write this in terms of what we are beginning with. And we were beginning with our acetic acid here. And so we just want to write its equilibrium process with water to produce acetate and hydronium ion. Now that we know that, we can then set up the Ka. So our Ka is equal to our products, right, the acetate and the hydronium ion, over our starting material, the acetic acid. And so that allows us now to do our ice table. And so we start with our 0.1 molar acetic acid. We have none of our products. Negative change for our starting materials. Positive change for our products. And we end up with that for our ice table. And now we solve for pH, right, where we're substituting back into our Ka expression. So our 1.78 times 10 to the negative fifth is equal to x times x, or x squared in the numerator, and then 0.1 minus x in the denominator. Right, our Ka is less than 1 times 10 to the negative fourth. And we have that starting material initial. So we can make our assumption that X is small. And so that means our Ka is then equal to X squared over 0.1, or that X, which equals our hydronium ion. Remember, that's how we're going to get at pH. That is equal to 1.33 times 10 to the negative second molar. We can then take the negative log of that hydronium ion concentration, right, the negative log of the 1.33 to the negative second, and we get a pH of 2.87. At this point, we're done with assumption checks. Which I know we are all happy about. So that's part A. Basically the initial starting point of the titration, and we're really just saying, what do we have initially then? We just have a weak acid, and it's just basically a weak acid question as far as a weak parent acid. Part B, now we've added 35 milliliters of the 0.1 molar sodium hydroxide. So basically you say now, the titration has begun. Right? Once we know that the titration has begun, this is now looking at a neutralization reaction. And that means that it is a mole game. Right? We got to get to moles of both of the materials. So our moles of our weak acid that we're titrating, we would start with its volume of 0.05 liters or 50 milliliters, and it was 0.1 molar. And so we end up with a value of 5 times 10 to the negative third moles of our acetic acid. We also need to determine then the moles of the strong titrant, namely the sodium hydroxide. At this point, we've added 35 milliliters or 0.035 liters. It as well is 0.1 molar. And so we end up with 3.5 times 10 to negative third moles of our sodium hydroxide. So that is what we are now using in terms of the neutralization reaction. So if we write out that neutralization reaction, we would have our starting material that we're titrating, namely the acetic acid. It's reacting with the sodium hydroxide. That's aqueous. and we are producing acetate, H2O, and then also we have sodium ions as well. So this is the neutralization reaction. Our sodium ion is a spectator. All right, there's no effect here on pH. We see it on the starting material side. We see it on the product side as the same. So that is not important. And so here is where we're filling in those initial mole values that we had above. This is a one-way reaction, so that means we have a limiting reagent, and our limiting reagent is the sodium hydroxide. These are reacting on a one-to-one basis, and sodium hydroxide has the least amount of moles, so that means it will run out first and go to 0. So we're using that as basically our change in terms of the reaction, that our acetic acid would decrease by that mole amount of 3.5 times 10 to the negative third, but our products would increase by that amount. And so we end up with a value for our acetic acid to be 1.5 times 10 to the negative third moles, and our acetate to be 3.5 times 10 to the negative third moles. And we have that same value for our water. The fact that now, we have now two things that are going to affect the pH. We have moles of the parent acid, namely acetic acid, but we also now have moles of the conjugate base, namely acetate. Those two quantities means that now we are actually talking about a buffer. We don't need that recognition. If we use our ICE table, we can still come to the correct answer. But if we do realize that at this particular junction in the titration it is a buffer, we could get away with then using the Henderson-Hasselbalch equation. So now that we have our neutralization reaction done, we can kind of go back to the question of, okay, now that we're done with the neutralization reaction, basically what does that leave me with initially? And that's basically now to solve for the pH. So we're basically back to, kind of question one as far as what do I have initially. And so in this case, I have both of those components. I have the 1.5 times 10 to the negative third moles of our parent acid, and I have 3.5 times 10 to the negative third moles of the conjugate base, acetate. The water here that's formed is inconsequential because water is a weak acid or a weak base, much weaker than the parent acid, acetic acid, or much weaker than the conjugate base, acetate. So that's why we don't have to worry about the water. It's so weak that we can just leave it out in terms of the pH calculation. So we now know what we have initially. That means we have two components. We have our moles of our acetate. I apologize, of our acetic acid. And we want to get that into terms of molarity. So we want to take that 1.5 times 10 to the negative third moles of the acetic acid, and now divide it by our value of 0.85 liters, or 0.085 liters. Remember, this comes from the 50 milliliters plus now the 35 milliliters that we've added, right? Where we have our 50 milliliters of the weak acid that we've added, and now we've added 35 milliliters of the strong base. And so our new concentration of acetic acid is 0.0176 molar. And we can do the same thing for our acetate initial, which would be equal now to its mole value of 3.5 times 10 to the negative third divided by that same volume of 0.085 liters. And that comes from the same idea, right? Because we're constantly doing a dilution throughout the question. And so if we calculate that, we have a value of 0.041 molar in acetate. So we have acetic acid initial. We have acetate initial. And because of that, right, again, that's why we have that buffer idea. We have both of those components initially. So in terms of our methodology, that means now we're looking at the equilibrium reaction. Remember, for buffers, right, that's in terms of the parent. And then we need to know our Ka, and what is that equal to? So we basically have the same reaction that we were looking at in part A. Where there is our equilibrium process, and our Ka would be the same in terms of those products over the starting materials. Right, that allows us now to set up our ice table. And now initially we have those mole values that we saw earlier, the 0.0176 molar, the 0.041 molar, and then we would say nothing for the hydronium. Again, we are treating each particular part of this as a new question. So that means that the hydronium ion initially is actually always going to be 0 in every single one of these cases. That's telling us our direction of change. And so we end up with our equilibrium concentrations with regards to X. That means now we can solve for our pH, right? Our 1.78 times 10 to the negative fifth was equal to 0.041 plus X times X over 0.0176 minus X. Again, we made the assumption in part A, and we can do it again here, right? Our Ka is less than 1 times 10 to the negative fourth, and we have initial starting material, so not only does the X drop out in that denominator, but it also drops out there in the numerator with regards to acetate. And so we end up with this 1.78 times 10 to the negative fifth is equal to 0.041 times X over 0.0176. And so we can solve for that X. Remember, X here is hydronium ion. That's where we're getting our pH. And so our X value here is equal to 7.64 times 10 to the negative 6 molar. That allows us to set up our pH. By just taking now the negative logarithm of that concentration of 7.64 times 10 to the negative 6. And that gives us a pH of 5.11. So that would be our pH for part B. Realize for part B, we recognized early on that it is a buffer question. But yet I utilized the ice table method to actually solve for this buffer question. Realize that, we could say that there is an OR to this. Namely, that the OR would be the Henderson-Hasselbalch. Right? Because we have a buffer reaction or buffer solution. Now here's the problem. I've said in class and lecture before that the Henderson-Hasselbalch is pretty sleek and sexy and students like to use it a lot. It's easy enough to recognize when a question tells you that it's a buffer to realize that, I can use the Henderson-Hasselbalch. During the titration, it's not as easy to recognize it's a buffer because that type of language is never present within the question. So students often get off key on the titration style question and like to use the Henderson in every single piece. Realize that there's only one portion of the titration question that you can use the Henderson-Hasselbalch, and that is right here. And that position, or that right here, is basically in between the initial and the equivalence point. And I want to stress that that's the only time that you can actually use it. I just want to stress it because I see this mistake so often. So if you can realize that this is a buffer, you can use the ice table method, which I've shown above, or we could use the Henderson-Hasselbalch. Which would look something like this. So our pH would be equal to the negative log of our Ka, right? Which would be the pKa plus the log, then the ratio of our conjugate, which was 0.041 molar, over our parent, which is 0.0176 molar. And so our pH would be equal to 4.749 for the pKa plus 0.367 for the logarithm of the conjugate over the parent, and our pH is exactly the same that we got above using the ice table method, right? They're really no different, but this will be an alternative to that particular process. For part C, we've now added 50 milliliters of the 0.1 molar sodium hydroxide. So again, now that the titration is going, the titration is running, right? This is still a mole game, right? This is based off the neutralization reaction, which is essentially giving us a new set of initial conditions. So that's why we got to employ this neutralization reaction, is basically just to get to the new set of conditions. What is that now initially? And that helps us to set up the equilibrium reaction, the ice table, et cetera, et cetera. So our moles of acetic acid, we determined that in part B, right? And that's not going to change. Initially, we began with 5.0 times 10 to the negative third moles of our acetic acid. Now, we need to find the moles of the sodium hydroxide. That's the strong titrant. Remember, that's really constantly changing. And so now we've added 50 milliliters of that 0.1 molar solution. So we find that this is a case where we have actually the exact same moles of sodium hydroxide as we do our acetic acid, what we're actually titrating. So our moles of acetic acid is now equal to our moles of sodium hydroxide. And again, just to remember what that's called, right? That's called the equivalence point. Where moles of H plus is equal to moles of hydroxide. So we have our mole values, and that allows us now to write the neutralization reaction. And so it's just like we had before. The neutralization reaction is not changing. We're titrating acetic acid, and we're titrating that with sodium hydroxide, and that's producing acetate, hydronium, and then also sodium ion. It's really not producing sodium ion because that's always there, where sodium ion here is going to be a spectator. So it has no effect on the pH. And so initially, we have our 5 times 10 to the negative third moles in both our starting materials. 0 moles in terms of our product. I know that can be confusing, having 0 moles of the product because of part B. But again, you want to treat each part as a new question. So in each part, with the neutralization reaction, we're really starting with nothing of the products. We're just looking at the starting materials. That's why also the initial starting material moles of the acetic acid doesn't change as well. And so in both our starting materials, we have the same moles. So technically, both are now that limiting reagent. Both of these are going to now 0 moles, and our products are increasing by that amount. That amount being 5.0 times 10 to the negative third moles. So here now we have only conjugate base that is left to affect pH. Water is there as well. I apologize if you go back to that. Shouldn't have said hydronium ion there in that neutralization reaction. That really should just be H2O plus. Just caught that error. So we have basically just left over now this idea of the conjugate base, right? That's all that's left now to really affect the actual pH. So that means when we go to 1, right, that means that now as far as our equilibrium reaction, this is now in terms of the conjugate base, since that's all we have left after neutralization. Which means now we have a KB, or remember we have to do the Ka-KB shuffle, right? Because it actually is a conjugate base. So the fact that we recognize as a conjugate base now allows us to set up the reaction as well as now the KB. So we would be starting with our conjugate base, the acetate, and now we would be forming acetic acid and our hydroxide as our product, right? Really a conjugate base style question. That means our KB would be equal to those products. Over our starting materials. And that our Ka times our Kb is equal to our Kw, right? That realize that all we have is the Ka for our parent acid, acetic acid, right? We need the Kb for now the conjugate base, since that is what this part of the titration has left over now. All we have left over is the conjugate base, so that's how we have to describe its pH in terms of the equilibrium reaction, Kb, and ice table. So the Kb will be equal to the Kw over the Ka, or 1 times 10 to the negative 14th over then 1.78 times 10 to the negative 5th. And so that Kb is equal to 5.62 times 10 to the negative 10th. So there's our Kb. We have our Kb expression, right? And that allows us to set up our ice table. Where we still have all of those components now slightly switched around with what we're starting with. Starting with our acetate, our products being the acetic acid and the hydroxide. And so now we're going back to that initial concentrations that we would need, right, for the acetate. So if we take our acetate concentration, we had 5.0 times 10 to the negative third moles of that over now 0.1 liters, right? Where is that 0.1 liters coming from, or that 50 milliliters? That's coming from the fact that we started with 50 milliliters of our weak acid parent, and now we've added 50 milliliters of our strong base titrant, and so we have an initial concentration of that acetate to be equal to 0.05 molar. So that's what we're plugging into our ice table. All the acetic acids have been neutralized, so there's none of that. And we have none of the hydroxide either. That's setting up our positive direction of change and allowing us to solve for equilibrium in terms of X. Again, X is what we're looking for. Here, now we get POH and then pH. So subtly different than in part B, where we're talking about, a buffer, or part A, where we're just talking about a weak acid. X was, in both of those cases, hydronium ion, so we could just go directly to pH. In this case, at the equivalence point, now we're actually beginning with the conjugate, namely the conjugate base, acetate, which means we're producing hydroxide, which allows us to get POH first and then pH. So that's where we now need to go as far as solving for our pH. Right, our Kb was equal to 5.62 times 10 to the negative 10th. Our acetic acid and hydroxide products are both X. And then our acetate is 0.05 minus X. Again, we can do the assumption motif. We're going to find that's always going to be the case with these weak, strong titrations. So this X is disappearing in terms of our starting material. And so we can solve for X, which is hydroxide, to be equal to 5.3 times 10 to the negative 6 molar. So now that allows us to get at pOH. And the pOH here is equal to 5.28. And then remember, pH plus pOH is equal to 14, or pH is equal to 14 minus pOH. And so we get a pH of 8.72. So, you know, for this idea of weak, strong titrations, the equivalence point is always a conjugate. Conjugate meaning that Ka, Kb shuffle. Right, it's always a conjugate style of question, right? We need to do a Ka, Kb shuffle. Also, something to notice about weak, strong titrations is the pH at the equivalence point is never 7. So we talked about in the strong titration how the pH is always 7 in terms of a strong titration, but in terms of weak, strong titration, that's not the case. The pH is not going to be 7. In this particular case, the pH is slightly basic at 8.72 because at the equivalence point we have basically a conjugate base that is now affecting the pH. Part D, almost there, people. End of the titration, we've now added 65 milliliters of the 0.1 molar sodium hydroxide. So we're still in the mole game. You know, the neutralization reaction. And, you know, what's left is the new initial conditions. Right? Just like we did with part B and part C. So our moles of our acetic acid is still the same. That's the 5.0 times 10 to the negative third moles. And our titrant has always been changing here. The titrant being the sodium hydroxide. And now we've added 65 milliliters of that 0.1 molar solution. So those are our 2 mole values, and so that's what's setting up our now neutralization reaction. Right, the neutralization is not changing. It's always the same. What we're titrating, the acetic acid, with what our titrant is, the sodium hydroxide. Right, we're producing our acetate. Our H2O. And we also have sodium ion. Again, that's our spectator. Not doing any chemistry. And so initially we have our new mole values. You notice if you look back at all of these neutralization reactions, as far as the initial standpoint is concerned, the only thing that's ever changing is our moles of sodium hydroxide. Acetic acid is always 5 times 10 to the negative third. Acetate's always 0. H2O is always 0. Now our limiting reagent is the acetic acid. So in terms of our final mole values, we don't have anything left of the acetic acid. Our mole value of the sodium hydroxide is decreasing by that amount, and the moles of our products are increasing by that amount. So we end up with 1.5 times 10 to the negative third moles of our sodium hydroxide. And then we end up with 5 times 10 to the negative third moles of our acetate, as well as our water. Even though we have a couple different bases here, really we have 3 of them. The sodium hydroxide is a base, the acetate is a base, water is technically can be base as well, but this is the strongest. You know, and even though we are forming acetate and water, even though these 2 molecules have the ability to produce base, hydroxide, right, they're really inconsequential to the actual calculation. The amount of hydroxide that acetate is based off of the KB, 5.62 times 10 to the negative 10th. The amount of hydroxide based off of water is based on KW, 1 times 10 to the negative 14th. The amount of hydroxide based by sodium hydroxide is the same, right? That it's dissociation. There is no Kb there. So that's why we get so much more of an effect with that strong base addition. So that means that this is just dissociation. So our sodium hydroxide concentration would be equal to that mole value of excess, the 1.5 times 10 to the negative third moles, over the new volume of 0.115 liters. which comes from the 50 milliliters that we started with in terms of the acid, and now we've added 65 milliliters of our strong base titrant. So now we're at 115 milliliters or 0.115 liters. And that gives us a concentration of 1.304 times 10 to the negative second molar. And that is really our hydroxide concentration. Our pOH would be the negative log of that concentration. And we get a pOH equal to 1.88. Our pH would be 14 minus that pOH, or 14 minus 1.88, and that gives us a pH of 12.41 for the data point here of 65 milliliters of the 0.1 molar sodium hydroxide being added during this titration. So, once you're past the equivalence point, pH is dependent on the amount of strong titrant left over. Or really, it's a strong parent type of question. So we've done the whole titration, and just to kind of summarize, there's always like 4 pieces to these titration. The first part is what I call the initial. And this is just a parent question. And to be specific, right, this would be, since it's a weak strong titration, this would be a weak parent question, like Ka, Kb. 2 is what I call, the in-between. And that's when we have a buffer question. 3 is the equivalence point. And now that's when it becomes a conjugate question. And then 4 is when we're now past the equivalence point. And now that's a strong titrant in excess question. Really a strong parent question. But it's really the titrant, and now it's in excess. So that's how you can break up each one of those pieces, as far as, part A, part B, part C, and part D is really those different pieces. All of them, as far as, the last 3, right, definitely involve that idea of the neutralization reaction. So keep that in mind as well, that we have a neutralization reaction that's occurring first, and then we have this type of buffer or conjugate or strong titrant in excess question. So now that allows us to actually start to plot our titration curve. So now we have all of the data points to sketch our titration curve. Our titration curve is in terms of in our x-axis or volume of the 0.1 molar sodium hydroxide. We had 4 different data points. We had 0, we had 35, we had 50, and then we had 65 milliliters in terms of those volumes that we're adding. We have our pH scale on the y-axis. So now we're just basically plotting the data points that we had from the calculations in parts A through D. Our first pH, and pH initial, was 2.87. So we could say maybe right around there. For part A, we went to 35 milliliters and we had a pH of 5.11. Right around there. And then at 50 milliliters, we were at a pH of 8.72. So maybe right around there. And then once we were past that equivalence point, which was the 8.72, we were at 65 milliliters, or at a pH of 12.41, maybe somewhere up there. So those are the 4 data points, and when we connect them, again, there's always this type of S-curve right around the equivalence point. So we kind of come up, and then we see this really steep increase vertical right around that equivalence point. And then once we're past, we immediately go up and flatten out there. There we go. So that's how the titration curve for a weak acid titrated by a strong base would look like. Getting into indicator, we would choose phenolphthalein because the indicator phenolphthalein has a pKa of 8. So we would get a color change at the equivalence point, right? Remember, we have that plus or minus 1 pH unit. So this would be the indicator of choice. And so this type of a sketch with this slow increasing beginning compared to the flat beginning that we saw for strong titrations is indicative of this weak strong. So we could think of now a general type of pH plot that we would see for weak strong titrations. So the picture for general titration curves of weak strong titrations. So we had a general curve for strong titrations, which was basically flat at the beginning, sharp increase in the middle, and flat at the end. And we find something subtly different with the weak strong titrations in terms of really the beginning piece of it. So if we have our volume of our strong titrant in the x-axis, right? Obviously our pH in the y-axis. Right, we find that these curves look subtly different. So if we have, a weak acid titrated with a strong base, what that's going to look like is much like we saw above, where you're going to have this increase in pH and then a sharp increase, and then it's going to flatten out over time. So it's this region here that's different from the strong titration. Right, that's usually flat, and the strong titration here, it's increasing. Or if we're titrating a weak base with a strong acid, we see the mirror image of that we start basic, but it's going to come down, and then we again have that steep curve, and then it flattens out. Again, once we're past that equivalence point. So again, we see that in that difference occurring here. Right, for the strong, it would be much flatter in that particular region. So that is our example of a weak acid being titrated with a strong base. With this example, as well as the strong example done in the prior lecture, realize that we've only done an example of an acid being titrated with a base. While the steps are all very much the same, please realize that you're also responsible to understand how to titrate a base with a strong acid. So look to the homework for those types of examples.